Assalamualaikum. Welcome to our Summer Technology Seminar and Musical Program organized by American Association for Bangladeshi Engineers and Architects of Silicon Valley. We are very much thrilled to have you here with us tonight, spending your valuable time Friday night with us, getting to know about the technology and also getting to know our AABEA members. We really appreciate you being here with us tonight, Friday night. So thank you and welcome. So before I start talking about the agenda and everything, I'd like to introduce myself. I know you already know me, but I am Aziza Rahman Rose. I am the Communication and Cultural Secretary for AABEA. And today's technical part I will be conducting. And I'd like to say a few words, what is the motivation behind tonight's event before we start to talk about the agenda and introduce our EC and everything. So the motivation behind today's event was very much aligned with our AABEA vision, which is we want our community to be involved and engaged in technology. We want our community to be interested about technology. It doesn't have to be that they're an engineer or a technical professional. We want everyone to be interested about technology, because nowadays that is just integral part of our life. So we want our kids, our younger brothers, sisters, our friends to be interested. So that's why we're going to have many seminars, forums, which will involve our community. And also, we want to have networking for the people who are already into the industry. So, as you see, by coming to this kind of seminar and technical forum, which is organized by AABEA, you can grow your network, which will help you in the future to enhance your career and have a bright future. So that is another goal. So all this vision of AABEA of Silicon Valley is very much aligned with today's event. We have speakers from Intel Corporation and Renesas Electronic here today, talking about some cool technology like Silicon Photonics future in data center, also talking about the MCA modulator, how we can have a bandwidth extension in an analog design. These are all cool topics we're going to hear from our speakers that we have tonight. And followed by that, we will have a panel session which actually focuses on what we say that, we'll get some career advice from our panel session today. So let's say you're a corporate personnel or you're an entrepreneur, you can get the advice or at least hear what our expert panelists have to say about how to grow your career in the particular field that you are in, whether you're a corporate or you're an entrepreneur yourself. So now I actually like to say introduce Sarwar Muhibhai here. Sarwar Muhibhai, a little bit introduction about him. He is right now he's a senior network consultancy engineer in Capgemini, and he has his bachelor's from Purdue, and he also has MBA from United States. And he is, which is very attractive to me, like he can speak 5 languages, which is very cool, Sarwar. So he is going to introduce our EC members here tonight for AABEA, and followed by that, we will hear from our president-elect for next year, Jamshed Rahman Bhai. And then we'll talk a little bit about what is going on currently, our current projects. So let us hear from Sarwar Mohib Bhai, and he will introduce our executive team. We want to request the executive team to be on the stage, those who are able to make it tonight. Thank you.
Can we have the introduction in 5 languages, please?
Oh, yeah. Last one.
Let's try. Good evening, ladies and gentlemen. Welcome to the AABEA event tonight. Thank you. Thank you. My name is Sarwar Mohib. Thank you, Aziza, for the introduction. Welcome again. I'd like to say welcome, Shagatam, Marhaba, Bienvenidos. Is at this 4 languages right there. So, thank you. I'm going to take the opportunity tonight to introduce the EC members here, as well as the sponsor, one of the sponsor here tonight. So I'll start with our current president. Unfortunately, he couldn't be here today. So we apologize for that. He had an emergency he needed to attend this morning. But his name is Muhammad Asaduzzaman. He's a founder and engineer, entrepreneur, business consultant, father, and biker. He has been working in the IT industry for almost 2 decades, located in the heart of Silicon Valley, San Francisco. He has worked on a wide range of technology, build, deploy, implement, and manage world-class Oracle eSystem Suite, cloud-based enterprise system in healthcare, auto industry, and e-learning, e-commerce, government, and public sectors. And he's involved in business technology and able to help young businesses around the globe to get off the ground. So once again, he couldn't be here today. So we wish him all the best to take care of his urgent needs. Next, we have our president-elect, Dr. Jamshid Ahmad. Can you please raise your hand there? Yeah, thank you. Thank you. He's currently a senior technical lead at Apple. Building software and services for iCloud. And he has worked in Microsoft, Twitter, and Intel in the past. I know we have some Intel folks here, past and present. So that's good, you know. And he holds a PhD in computer engineering from Syracuse. His research was on AI-driven self-healing computer networks. He's passionate about networking and collaboration with others in technology. So now you know him. So you have a problem with iCloud, you know who to go to. And also, if the AI start to steal your job, you know who to go to as well. So thank you for being here tonight. And next, I will go with Miss Aziza Rahman Rose. She already introduced a little bit about her, but just a few more details. As you know, she's working at Intel Corporation as a technical program manager for subsystems design and IP projects since 2014. Prior to Intel, she has worked in Broadcom, Seagate, and startups in Southern California and in Bay Area. She earned her bachelor's degree in computer engineering from Georgia Tech and master from Cal State East Bay. I guess I get to find out that we're alumni to the same university. That's where I got my MBA, Cal State East Bay. So that's great. Apart from her technical abilities, she is also an artist. She is very skilled in singing, and we definitely gonna find out about her skill set on that tonight. And I'm sure you will all enjoy that. So, yes. And in her leisure time, she likes to spend time with her daughter and which she feels is the most relaxing and rewarding time of the day. So that's all about Miss Aziza Rahman Rose. Thank you. Next, we have the treasurer of AABEA, Mr. AKM Dulal. Okay. Let me ask you, does he really need an introduction here? I'd rather say, who here doesn't know him? I think that would be a small number of hands going up there. So regardless, he's the treasurer. Welcome tonight. And he has, over the last 2 decades, having working experience in semiconductor, networking, and VoIP telecommunication in both private and public sector. He is active in various non-profit organizations in Silicon Valley. He is proud to be involved in AABEA to build bridge between US and Bangladeshi engineering professionals for knowledge transfer in various fields in technology. And that's what's happening tonight. So thank you, Dulal Bhai, for being here tonight. Round of applause for him. Next we have the secretary, SM Sohailjaman. Can you raise your hand? Welcome to the program tonight. He is a engineer at T-Mobile currently, and he is, he graduated from Buet in Bangladesh, now the most prestigious technical university in Bangladesh, as well as he has an interesting background. He did his MSc from University of Stuttgart in Germany. So I bet he speaks good German as well, right? That's good. That's one language I don't speak. Good. It's good to have complementary skill set around in the community. So and he also recently got an MBA from University of Illinois Urbana-Champaign. So congratulations on that. He throughout his tenure in AABEA, he's dedicated to connecting Bangladeshi technologies around the world and empowering the next generation of engineers and architects. Thank you. Next, we have one of the EC member, and I see he has a banner too. So if you want to know who that is, you can just look there. You don't need to raise your hand. You are exempt from that. Mr. Shohidul Islam, he's an EC member of AABEA, Silicon Valley chapter. He's a staff application engineer with RF and optical chip design. He has 20 years of engineering experience. In the past, he worked at Bangladesh Power Development Board and many other companies. He's also working as a real estate agent since 2020. So if you're looking to buy or sell real estate, you have a guy right here. So he earned his MSc in telecommunication and microengineering from Cal Poly Pomona, same as Dulal, if I'm not mistaken. So that's all the EC member. Then we have advisor. Mr. Jahangir Dewan, he's also a big sponsor for tonight's event. So welcome to the program and thank you for your support for this organization and for the event tonight. So thank you so much for that. Mr. Jahangir, he's got his PhD from Deakin school, right, and an ABA from Cornell, right? So very highly educated. He's a founder and president of CEO of SBIT Inc. in Silicon Valley. He's a director of engineering in a stealth mode AI chips and system startup in Mountain View, California. So if your job gets stolen, you know another guy who you need to reach out to with the AI, right? That's the fear nowadays they have in Silicon Valley that AI is gonna take over everything. We'll see about that. But it's good to be working on the top-notch, technology. So, he's, for his, what do you call, his startups, his, for the SBIT Inc. He has client base in Bangladesh. Many startups there and many universities. There's a whole lot of universities. I'm not going to go through all of that. But he has clients in USA, Meta, Facebook, Microsoft, AMD, AABEA-SiliconValley-Summer, Elevate. These are top-notch universities he's working with. So congratulations on that, working with the top Silicon Valley companies. So with that, I want to thank you for coming here, and round of applause for all the panel here tonight. And then we will have a cultural section later tonight, and I will introduce the artists at that time. They're getting ready right here, and then over there as well, so we'll do that. But that concludes my presentation. So I'll pass it over to you, Aziza. Thank you, everyone.
Thank you, Sarwar Bhai. That was a really good introduction to our EC members. So now I'd like to invite Jamshed Rahman, President-elect, to come on the stage and tell us more about AABEA goal and some of the future activities when he's going to be in the office. So, Jamshed Rahman Bhai.
Hello. Is that too loud? It's okay. All right. Thank you. Can we have another round of applause for Aziza? She is really great. I just want to say congratulations. She's only been here like a few months. She joined our EC, I think last year,
August.
like end of last year, and now she's already doing events and getting people together. So thank you. Great stuff. Thank you. Welcome everyone. So happy that you guys are here. I'm not going to say too much. I'll be brief. We're going to have a really fun event tonight. A lot of good tech stuff that we're going to talk about. We have speakers. We'll talk about Silicon Photonics, and then modulators and amplifiers, highly technical stuff. And then we'll have panel speakers. We will talk about career development. We will talk about, what is the other one? I remember entrepreneurship, and then also like career advice for recent graduates, stuff like that. So everybody will have something for all of you. I do want to thank the EC folks, especially Aziza Shohid Bhai, who is, where did he go?
Yeah.
Oh, there you go, yeah. And they worked really hard to organize this event, and our senior advisors, Jahangir Bhai and Shaq Hussain, really helped us out. So thank you to both, all four of them. Now, just to give a little bit of history, AABEA is the American Association of Bangladeshi Engineers and Architects, and the main focus of AABEA is to build network between Bangladeshi engineers here in the USA and also doing professional development. So we do that mainly by a few focus areas. Number one, we do tech events like this, where people come together, and that's more chapter-wise. We're the Silicon Valley chapter, and we're doing our events. There's other chapters, they do their events. We also do conferences. That happens every 2 years, and that's when all the chapters come together. We have about 9 chapters across the US. We have New York, LA, Michigan, DC. There's many chapters, and there's lots of engineers and architects that are part of each of these chapters. And finally, we do projects, and Aziza is going to talk about some of our projects, and they're international projects. We've done things like training, we've done computer labs, really big stuff that happens in Bangladesh and also here. So it's really good to be part of AABA. I'm really happy to be the next president and do many more events next time. Cool. And finally, I'm going to talk a little bit about what we'll do next year when we have our new EC people doing active stuff. I was talking to one of these members today, and we want AABA to be the platform for Bangladeshi engineers where they can grow from, right? So we're talking about next generation engineers. They're already in schools. We have really good partnership for Berkeley Student Association. We've done 2 events with them before, and we want to do more. And this will be more like resume review, internship fairs, science fairs for younger kids. So we want to focus on more technical stuff for the next generation Bangladeshi engineers. For professional career development, we want to do tech events. If you're thinking of career change or moving into a new job or learning new technologies, we will have workshops to do that. That will start next year. We will have interviewing workshops if you're looking to change your job, and also focus on AI. We have Dr. Shafiq Abedin. He's an ML engineer at IBM. He is not here yet, but we're trying to get a workshop to do AI training and focusing on that next year. And then finally, we're going to continue doing our great projects that we do internationally, Aziza again, we'll talk about that. But finally, I just want to say thank you. It's going to be good, and I can smell the good food that's already out there. So I hope everybody has fun. Is everybody having fun? Yes, excited? All right, let's get it started. Thank you. Let's do it.
Thank you, Joseph, for your speech. Yeah, we get to know that what some of the upcoming activities will be by AABA, and I'm sure we all are very excited about that when Joseph is coming as a president. So, actually, Shimabhai had sent us a video, but we were unable to play that video. But I would like to say his message. He said that he's very happy that we all have gathered here today for the event, and he is definitely missing this nice event. So he just wanted us to know that, and he has thanked all of you for being here tonight with us. So that was from Shimabhai, and. I'd like to talk right now about some of the ongoing projects, and then thank our sponsors who are here with us tonight also. So let me first talk a little bit about the ongoing activity. So our major activity right now, what we have is called IT Village project, which is based in Bangladesh, and we have so far been the main goal of the project is to actually have the training center, computer training center for the unprivileged people and children of Bangladesh, where they can get some computer trainings. And it is about the basic computer skills such as Word doc, Excel, writing and reading emails. So AABA of Silicon Valley, we are trying to facilitate some computer center through this particular project called IT Village project that will have some facility for unprivileged folks who are in the rural area of Bangladesh mostly, and so that they can go to those centers and get some free trainings of how to use some of the basic software such as Word doc, Excel, and email writing. We also like to focus on children specifically, those unprivileged children, and provide them with the free classes. So our focus is very much on the children, also not only on adults. So to have this project successful, we've been collaborating with a lot of non-profit organizations based in Santa Clara, and also some of the companies of Bay Area, where mostly the founding members are originally from Bangladesh. So one such member is with us here, Jahangir Dampai, and also I just received this, so I'll talk a little bit about Mrs. Khan here. She is also helping us with that IP Village project, and I'll just read it out because I just received like a minute ago. Thank you, Sitaranti. Thank you for being here. She and her husband is always a big champion for AABEA of Silicon Valley, and we really appreciate it, Auntie. And let me just read it out, what I received. So I'm just reading from the paper. So Honorable Chair, distinguished guests, AABEA executive members, Assalamu alaikum and good evening. Thanks to Jahangir for a wonderful introduction. I'm very much delighted and honored to be here attending as a guest. My late husband, Dr. Khan, and I have been involved in AABEA activities since 2002. In 2002, we have sponsored a VLSI lab at East West University, and this year, the Imdad Sitara Khan Family Foundation has established Dr. Imdad Khan VLSI Design Lab at Dhaka University with the support of AABEA. So thanks, Auntie, and your family. So we also now like to, as you hear that this project is ongoing, so we would need your support. Whichever way is possible, please support our IT Village project in Bangladesh. We'll be humbled to have any advice from you or any financial help from you. So that is currently ongoing. So, and after this, I'd like to thank our sponsors, because without them, today's event will not be possible. So we want to wish all our sponsors the best in their career. And we have sponsor Jahangir Dampai, gold sponsor. Please have a round of applause for Jahangir Dampai and all the sponsors. And we have myself and Nazrul Islam Bhai, Mohammad Zaman Tiku Bhai, Shoaib Islam Bhai, Jamshed Bhai as well. I will be talking just a little bit about each of the sponsors, because without their enthusiasm, without their support, this event will not be possible. So first, Jahangir Dampai company SBIT he's a founder of SBIT, and they provide the VLSI support, as you heard in here in United States and also in Bangladesh. So thank you, Jahangir, for your support for AABEA. And he has actually helped as an advisor for this event also, which I personally want to thank him. Thank you, Jahangir. Next, we have our sponsor, Mohammad Zaman Tiku Bhai. He is currently in Bangladesh, but he is a real estate agent, and he is also a loan advisor. So for your next home purchase, please reach out to Mohammad Zaman Tiku Bhai. And thanks, Tiku Bhai, even though you're not here with us, we'd like to thank you for your support. And then next we have Mohammad Nazrul Islam Bhai. Yes, please stand. Nazrul Islam Bhai is here. And from the Travel Canvas. So he has a couple of founding companies. Travel Canvas, you can book your ticket, you can plan your next vacation, hotel booking, planning a next vacation, or going back to Bangladesh. You can always reach out to Nazrul Islam Bhai. And also they have a Tech Muzi, the IT service company, where you can get some cybersecurity help and as well as some UI and UX design help. So thanks, Nazrul Islam for your support. We appreciate it. And then again, we have Shoaib Islam. He is an EC member, and thanks Shoaib for helping with the event tonight. And Shoaib also is a real estate agent. So for your next purchasing of your home or selling your home, please reach out to him. I'd like to thank Shoaib personally for this event. Thank you for helping. And thank you for your support. And this is me. As Sarah Bhai said, I have a passion for music. I've been learning music since I was 5 years old. I went to China to have a major in Rabindra Sangeet. So this is my music channel. Through my music channel, recently I'm trying to have new music added. So please subscribe to my channel. And I was honored to sponsor this event because AABEA is very close to my heart, and also this event. So I'm honored to sponsor this event myself. So also like to thank Jamshed Bhai. Jamshed Bhai, we don't have your slide here, but Jamshed Bhai has supported this event with his sponsorship, and also Shah Hossain Bhai. Thanks to both of them for supporting this event. So now we would like to start our event's first section, which is we have the speakers from two of the leading technology companies, Intel and Renesas Electronic, speakers from those two corporations here tonight. First, I want to introduce you to David Gold. David Gold is my manager in Silicon Photonics. Right now we call it an IPS, Integrated Photonics Solutions team in Intel. He is the manager for test engineering team, my manager and a great mentor. And David will be talking about Silicon Photonics' future in data center industry. Before David talks about all the cool stuff about Silicon Photonics, I'd like to say a few words. We all know, I think, about the Moore's law. If you hear Intel, you know Moore's law, Gordon Moore's law. And Gordon Moore's law is the observation which says that every 2 years, transistors will be double in a circuitry. So this puts us into the pressure where designers always want to come up with a short scale design. And Silicon Photonics certainly can help in that. So one of the benefits of Silicon Photonic IC, or we call it PIC, Photonic Integrated IC, it serves that purpose. It gives us a short scale design. And other than that, of course, it reduces power and gives us a faster data transmission. So enough about the Silicon Photonics from me, and now we like to hear from David Gold. David has a 25 years of experience in industry in Silicon Photonics, and I'm very honored that David is here with us tonight to say more about the future of Silicon Photonics in data center industry. David Gold, ladies and gentlemen, please give a round of applause.
All right, first I want to thank Aziza. Not only is she a good person to have in the group, but she's doing an excellent job up here. And I want to thank her for inviting me here to talk about this. It's, I must say that it was a little hard to gauge, what sort of level I should have this talk at, but seeing as there's a real mix of people with very smart, very experienced engineers, feel free to tune out if you've seen it, but hopefully there'll be something new that you see or pick up, or we're always looking for new ideas. And so I kind of planned this out as what is going on, what has been going on in silicon photonics, and maybe more importantly, where is it going? And when you say where is it going, what you really want to find out is, well, in any big technology leap, there's always a motivator in it, and there's some sort of what they call the killer app. And it's like the killer app for computers really was Excel, right? I mean, the spreadsheet programs turned on the bankers, and that's where when the money started pouring in. So there's always a killer app, and so the question is, has silicon photonics, which has been around for a few years, for well over a decade now, has it found its killer app? Because there's a lot of competitors to silicon photonics that can do the same, in a cheaper way. And so silicon photonics really needs to write its own story. So let's just start with that motivation, with that theme. Let's see how that changed. Okay, so as for an outline, I just want to start real basic with what is silicon photonics. It's really just a marriage of technologies. It's a marriage of electronics and photonics, or playing around with photons. And then I'll talk about this technology motivator, or the killer app, as I mentioned. And then I want to step back just a little and talk about the fundamentals. How do you fabricate silicon photonic products? And then finally, and probably most importantly, where is silicon photonics going? And if you haven't heard about co-packaged optics, and I'm sure many of you have, if you've been in this wonderful industry for a while, you're going to be hearing about them because they really are the future. Okay, so with that, let's just start with the simple stuff, which is what is silicon photonics? As I mentioned, it's a marriage of electronics, so you can think something like modulators, things that modulate signals, detectors, things like that, and photonics. So photonics is lasers, waveguides for photons to travel down, photodetectors, things like that. And you take those all and you marry them and you build them on a silicon chip. And see, I've got a couple of example pictures up there, and when you put them onto a silicon chip, you can develop things like transceivers. So a transceiver is a transmitter and a receiver put together into a single module. And you can see if you take the lid off that transceiver, on there is a silicon chip as well as plenty of standard electronics, and that's silicon photonics. You can also build products like sensors. In that middle picture on the right is a LiDAR module that Intel built with Mobileye. And this has been demonstrated in real cars driving through downtown Jerusalem. So, that chip in the center of it works very, very well. And so those are the types of products you can make when you marry electronics and photonics. And actually photonics gives you some advantages because there are certain properties of photons that you just don't have access to with electronics, such as something like light polarization. So what is, where did silicon photonics come from? Well, what it really does is, its real advantage is that it brings the photonic environment, which is traditionally a very hard technology, it brings it down to the standard electronics industrial environment. So it leverages decades of CMOS wafer scale fabrication knowledge. And we've essentially adopted the processes of the electronics industry to develop these products. And so, as I mentioned before, you also have some advantages in applications where you can use the properties of light to gain advantages in computation, communication, sensing, things like that, imaging. And so the main products, again, are data centers. That would be transmitters and receivers. These are the things that power the internet. You generate your signal on a computer, you send it out over an optical fiber, and it's received, at a data center, transmitted to some other receivers. And then sensors in LiDAR, biomedical, automotive, many fields, Silicon Photonics sensors are. But I'm going to focus this talk on the data center part. Okay, so now let's move on to the killer app. For many years, for well over a decade, the internet has been sort of marching along according to what we would think of the standard Moore's law, and that technology, electronics and photonics have been able to keep up with. Where, if you think of these sort of general purpose cloud-based applications like video streaming, social networks, search engines, and e-commerce, those all have been advancing at a very, fairly steady rate. And we've been able to keep up with that technology using, faster and faster modulation techniques, various tricks that you can play where you're, mixing signals, say, with different polarizations or different colors, different wavelengths, things like that, to get more and more capacity onto that same fiber. And so those were all driven with what are called 100 gigabit per second per lane. So that means every laser that's sending out a signal can send that signal out over the Ethernet at about 100 gigabits per second. But now we're sort of reaching a point where we're going to higher bandwidth systems, 200 gigabits per second per lane and beyond. And maybe more importantly, what we're really up against is the new generative AI that's coming. Well, it's really already here. And when I talk about generative AI, I'm talking about artificial intelligence, machine learning, large language models that have applications in everything from robotics to medicine and chemistry. And so if you look at the plot on the right, I call this the AI challenge. And what we're looking at there is this is a plot of how much computational resources are needed to train the AI systems. And you can see, hopefully you can read that, but way down in the start, we're decades past, and right about where that blue section and the slope changes rapidly, that's 2010. So we were progressing along sort of in the background with AI for many years with simple algorithms that tended to be limited by the computational power that was available. And then all of a sudden around 2010, deep learning came in, new types of processors, GPUs, so these are processors that act in a parallel way rather than serial. And TPUs, these are ASICs that are developed specifically for AI. That's a tensor processing unit as a TPU. And other processors have been developed specifically for AI applications. And because of that, we're no longer computation limited, and the slope of that has just taken off like a rocket. And that's the AI challenge. How do we keep up with the amount of processing power and data transfer that AI needs? And so what I'm going to propose is that this is where silicon photonics is going to find its killer app. So how do we scale this throughput while and bandwidth density while keeping it power efficient and economically viable? And in my mind, really the only way you can do that is by high density photonic integrated circuits. Okay, so now let's step back a little and talk about the fundamentals. And this is my area. I'm really a test engineer, but you know I know enough about the fabrication process to describe it. So let's talk about the fundamentals of how silicon photonics works. And so what you do is you leverage the industry standard CMOS CMOS processing, and you take integrated circuits that transmit, modulate, and detect, and you develop integrated circuits that modulate, transmit, and detect light signals. But anybody that's taken materials science, in college, well, maybe not anybody, but many people know that you cannot make a laser from silicon. So what is this with silicon photonics? Well, I'm not going to go into the detailed physics of why you can't make one, but essentially it has to do with the band gaps, the electronic band gaps in the material. Silicon has what's called an indirect band gap, and if you try and pump it like a laser and stimulate photons, you'll generate heat and no photons. There are other materials called 3-5 materials that will laze when you electrically pump it, and that's what is used to make the laser that powers the silicon photonics. So that is the secret sauce of silicon photonics. What it is it's a heterogeneous, or two materials. You're mixing two materials, a lasing material and a non-lasing material, to make a silicon photonic product. And so here's how they do it. This is the secret sauce. It was invented really by UCSB, but adopted and shepherded through to industrial scale by Intel. It took them about 15 years to develop it. But essentially what you do is you take a wafer that has material that can laze and a silicon wafer, and you fuse them together. And by fusing them together, you temporarily fuse them together, and then you put a pattern on it using a standard CMOS process. And by putting that pattern on, which forms the integrated circuit, what you do is you offer all sorts of advantages in that the light can go from the silicon into the active region where the light gets amplified or generated and back again without significant loss. And there's many other advantages to doing it that way, but this turns out to be the secret sauce of silicon photonics. Okay, so you can't just develop a laser through that process. You also have to develop everything else in the circuit to get to make silicon photonics products, and that means that you have to be able to develop lasers, modulators, they call them data encoders here, you need light detectors, and then they call, they say MUX and DMUX. Well, that's for combining signals or separating signals, things like that. And you have to develop all of those to develop a chip that actually performs some sort of function. And so the major processing areas involved in that are you need epitaxial deposition, the fabrication or etching, then there's metrology or measurement of all those processes. You need people doing statistics on them. And then you need to put that all together and do the testing and the test development. And I highlighted that because that's my area. That's where we see whether the product actually works. We see what the truth is. And then, of course, you have to take that chip and package it and see how reliable it is. Is it going to sit in a data center for 15 years and still work? And so on the right-hand side is my area. We develop tests at both the wafer level, which is a huge advantage of silicon photonics. We also develop them at the chip level because not everything can be tested at a wafer level. And there you see, in order to test at the chip level, we often have to make an evaluation board, and that's where Aziza fits in. She is the owner of our eval board fabrication manufacturing and fabrication. She's the one that gets it done so that we can do the testing like that picture down in the lower right. Okay, so given that process, you make this little integrated circuit. What are the advantages? Well, essentially everything gets better when you put it on a chip. You have you have lower losses of coupling between the laser and the rest of the chip. You have very high accuracy of the wavelength of those lasers. You're very flexible in terms of choosing what bandwidth you want to play in by choosing what gain material you use. You can use different types of optical amplifier. There are many advantages. I won't go through them all, but essentially the power gets smaller, the reliability goes up. You can work at wafer levels, so work in high volume manufacturing. And maybe the biggest advantage in terms of economics is if you compare them to a standard optical system that's not on a chip, you can replace literally dozens and dozens of components by a single chip. And that offers a drastic increase in your reliability. Okay, so it doesn't come for free, and it requires a highly skilled team. And so this is where, Intel is always looking for good people. And we need people, that know everything from chemistry, to computer science, to physics, to mechanical engineering. All of these fields are useful and valuable to do all the tests. There are literally thousands, maybe tens of thousands of steps that are involved in making one of these chips. Okay, finally, where is silicon photonics going? So I talked about on that cloud, the upper cloud on the left, I talked about 100 gig per second per lane Ethernet going to higher data rates, say 200 gig per lane and above. The problem with that is that anytime that signal encounters a copper trace, there's a lot of radio frequency or RF loss. And so in order to make the jump to higher bandwidth channels, we've got to overcome that RF loss. So how do you do that? Well, the way you do it is you evolve from the system on the upper right there to the one on the lower right. And what the evolution there is taking it from our standard package where the light, the transceiver is plugged into the card, and then it goes through a long line of copper before it gets to the ASIC switch. You take that and you keep moving it closer and closer to the ASIC switch until it's literally one package with the ASIC switch, and that's why they call it co-packaged optics. So you can see the copper in each of those is getting smaller, the copper path is getting shorter and shorter until the optics are actually married to the ASIC switch there. And so you save power by improving the bandwidth density and getting rid of that RF loss. So in 2020, Intel did an initial demonstration of these co-packaged optics and moved from the front faceplate version of transceivers down to what are called co-packaged optics, the third drawing there. And this was the first time that, you know, people had talked about this in industry for probably more than a decade. And this was the first real demonstration of a co-packaged system. And you can see there's some live data pictures there, and all those, what they call eyes, are showing high quality data there. So this represented a 1.6 terabit per second bandwidth, which was a 40 times improvement in the bandwidth density and a 30% improvement in energy efficiency compared to the traditional pluggable module, which you see in the upper right there. And then in 2024, just 4 years later, Intel went beyond that demonstration and did a demonstration of what they call optical I/O co-packaging. So this would be like two processors talking to each other optically rather than electronically. And it was really the first ever fully integrated optical compute interconnect co-packaged with a CPU. So here you have a Silicon Photonics chip co-packaged with a standard electronic CPU running live data. And this is the type of architecture that's needed for the AI systems and the high performance computing applications. It was a 4 terabit per second bidirectional demonstration, and it took only 3 picojoules per bit, or actually under 3 picojoules. And so this OCI chiplet can be packaged with all sorts of next generation processors, CPUs, GPUs, IPUs, and other systems on a chip, and offers very high bandwidth. The Silicon Photonics chip itself is a picture of it is on the far right there, and that's about the size of a pencil eraser, something like that. Those were real proof points in terms of meeting this AI challenge, because they offered real-world demonstrations of the technology, and now, you know, it's sort of up to Intel as well as some of the other players in the industry to really bring this type of technology to a high-volume manufacturing point. And I think that this, this type of technology is really the only thing that is capable of addressing this AI challenge that we're coming up against, because there's no other technology out there that can offer anywhere close to the bandwidth for the economics that Silicon Photonics offers. And so with that, thank you.
Thank you, David. It was a very insightful speech about Silicon Photonics. I myself didn't know so much, actually. You know, when you work, you just get so much used to it, becomes your second hand, like you feel like you know everything, right? But it was just a summary of a lot of cool stuff about Silicon Photonics. That was a great presentation. Thank you. And actually, you know, I worked in the PSM4, the first module that Silicon Photonics team of Intel has created. The first module, it was 3 of us, 2 of my other coworkers and me. So I always take pride into that the first module of PSM4, I worked in it, and it's in my LinkedIn profile if you see that. So thank you, David, and he's a great manager and mentor. I'd like to say my thanks to David for being here with us tonight. Thank you, David. And now we like to hear one more tech talk from Evan Croter from Renaissance Electronic. Even has over 10 years of experience in design, starting from fiber optic, coherent communication, and today's topic, he will be concentrating on bandwidth extension, particularly in the type of driver that we use, MZF driver. So let us hear from Even Product, ladies and gentlemen.
Thank you, Aziza, and thank you, AABEA, for inviting me to speak here. I'd like to share some of our work at Renaissance, and it fits very nicely with Jay's presentation on a more silicon level. So, bandwidth extension techniques and largely linear drivers. First, I'm going to talk about some of the industry trends that we see and the need for such drivers. We're going to discuss some of the typical requirements that are necessary for these drivers, how we design them, some of the voltage breakdown and swing requirements, and then I'm going to introduce three classical or sort of standard techniques that we use in the industry to achieve the necessary bandwidths that are needed for the data rates. And then I'm going to conclude with some of our recent drivers that we have currently in the market. So what is on a higher level? Optical transmitters typically employ either direct or indirect modulation. And direct modulation basically means that we're essentially directly modulating the laser. Or an indirect modulation basically means that we're modulating we're driving a modulator, which is modulating the optical signal, which is then sent to on the optical fiber. In an indirect modulation system that we have here, or external modulation, the modulated signal usually features narrower spectral bandwidth and a higher extinction ratio, and therefore it's able to reach higher data rates and higher order of modulation formats. These Alexander modulators are typically designed in lithium and D5 semiconductors such as lithium niobate and indium phosphide. And more recently, we see a lot of them coming in silicon and silicon photonics. Where I work particularly is on the field of basically on the electrical optical interface, which is mostly on the electrical side, which is the linear driver that is driving the Alexander modulator. Essentially, data coming from the DSP and DAC is at a low voltage swing, typically about 2.3 volts peak to peak swing, and we need to amplify it to 2 to 4 volts peak to peak in order to fully switch the Alexander modulator and modulate the optical signal. These drivers are typically implemented in silicon germanium by CMOS technologies, and I'll show you that in a second why. But there are many different technologies that can be used as well and have been used in the past. So a standard silicon germanium HBT or heterojunction bipolar transistor typically exhibits these kinds of curves. Here I show a list of foundries and their FT, or basically transit cutoff frequency versus the breakdown voltage DVCEO, and this is known as the Johnson limit, or the Johnson limit curve. And if we plot each of the foundries technologies on the same curve, we see that they all pretty much follow the same pattern. The FT is inversely proportional to the breakdown voltage. As the breakdown voltage goes down, the FT goes up, and it's in a logarithmic fashion. The typical technologies that we use are in the 300, 350 gigahertz FT. And as a rule of thumb in the industry, the bandwidth requirements for a driver should be less than FT over 3, so 3 times the FT of the technology. That's where first we select the technology. So for typical, like, let's say current 128 gigabaud application, FT of around in excess of 300 gigahertz is a suitable technology, and therefore the breakdown voltage is limited to about 1.5 volts. Typical requirements for a modulator driver are basically the highest strain is on an output stage. It requires a large voltage swing on the output, and therefore a larger current swing. And in addition to that, it requires to have a high gain and bandwidth, and all that simultaneously. So there's always a trade-off between gain, linearity, and bandwidth. Linearity is one of the key parameters that we design for, and a larger swing. So typically, to swing like this, for example, a Silicon Photonics modulator or an indium phosphide, we need more than, let's say, 2 volt peak to peak single-landed swing. And depending on the data rate, we need a certain bandwidth, which is essentially given by like Nyquist theorem. And so, for example, for 128 gigabaud target system, we target, say, 64 gigahertz of bandwidth. The gain, typically we want to concentrate a lot of the gain towards the output of an amplifier. This increases the linearity of the chain. And finally, we must ensure that the reliability of the amplifier is consistent, that the transistor does not exceed its breakdown limits, which are basically called DVCEO and DVCEO. And over a long period of time, for example, 10 years or so, once the amplifier is actually deployed. So our typical approach to designing such an amplifier is to first satisfy the voltage swing and linearity requirements, and then use techniques to increase the bandwidth and achieve the necessary data rate. So starting with the voltage swing, for a typical, let's say, common emitter amplifier, which is a textbook amplifier shown in the schematic here, with the, let's see, 300 plus gigahertz FT technology, we are only limited to about 1.5 volt peak to peak swing, which is not enough typically to swing for like with a Mach-Zehnder modulator. And therefore, we need to mitigate this issue, and how we do that is through, let's say, cascoding. There are various types of strategies, but one of them is to have a cascode device on top of a common emitter device or a common base device, which essentially increases the linear swing of the output stage to an acceptable level. And there are various types of cascodes, and the two most common are static and dynamic. In a static cascode, the common base device, base terminal is constant, whereas in the dynamic cascode, there's a feedback network given by the resistors and capacitor over there, and the base is modulated, and thus the swing is divided actually between the two devices, between the top and bottom device, and thus neither device exceeds this breakdown voltage. And with these devices, we can see that in this curve, we can achieve about 2.5 volts peak-to-peak maximum swing, which is well in excess of our desired 2 volt peak-to-peak. So, once we acquire our proposed design topology, then we look for techniques to increase the bandwidth. So the first technique is Miller suppression, or basically the Miller effect is a well-known effect in transistors. The feedback capacitor between the collector base appears to be multiplied by the gain of the amplifier and added to the input capacitance of the amplifier, and therefore limits the bandwidth and is the dominant pole in the circuit. One way to mitigate this effect is to add low input impedance stage, such as a common base, which reduces the voltage gain of the common emitter, and therefore reduces the Miller effect. There are other ways to compensate for Miller, but this is one of the most common. And the trade-off here is obviously power consumption. So you can see on the curve here that a common emitter device exhibits, let's say, less than 30 units of bandwidth, whereas the common base with common emitter has quite a bit of an improvement. The second technique I'd like to introduce is buffering and scaling. The topology of the individual stage of the common emitter stage can be buffered with an emitter follower, and between multiple common emitter stages we can add an emitter follower which can be scaled in size and therefore reduce the input capacitance further of any previous or subsequent stages. And here we show the different emitter follower, and we have 3 transistors, emitter follower, common emitter, and common base. And here we're actually employing multiple techniques, both buffering and scaling and Miller suppression. And finally, multiple emitter followers can be added and can be used. Again, the trade-off here is power consumption. And here's a typical, let's say, improvement that we can obtain. You can see with the emitter follower, we can increase quite a bit the 3dB bandwidth from the basic building blocks. This is typically very much used everywhere. And we can improve even further. It also works with the dynamic cascode as we introduced earlier. And furthermore, we can even go further by adding a triple cascode, as shown in the diagram, with the feedback resistor. And that one has all the benefits that we've introduced so far: dual buffering, Miller suppression, and shared voltage swing for reliability. And the third technique I'd like to introduce is something called inductive peaking. Inductive peaking is basically essentially using an inductive element to tune out circuit capacitance and nodes and increase its bandwidth. At each node there is typically a capacitor and a resistor, and that capacitor to a certain extent can be compensated with some inductance. A typical inductor is placed in series with the load resistor RC here, as we can see in the diagram. This is called shunt peaking. The typical improvement that we can obtain from this is about 1.5 times the bandwidth. And a more complicated structure, which is known as a T-coil, can be also used, and many others, of course, and essentially, which is essentially a higher order filter. And it has a maximum theoretical extension bandwidth of 2.8 times. And here we see how they work in practice. The common emitter stage is compared to the shun peaking and to the T-coil. And we can see that in each case we get the close to the theoretical maximum extension. Finally, this is some of our drivers that we have developed and some that are under development and are future. We have multiple generations, from 100 to 800 ZR, 100G to now 800 ZR, both linear and open collector and back-related drivers. So, in conclusion, direct and indirect modulation and fiber optic transmitters add the requirements to the electrical components, and the most critical is the linear driver on the transmitter side. It requires a high voltage swing, high linearity, high bandwidth, and gain, all simultaneously. Silicon germanium by CMOS technologies are typically used in conjunction with clever circuit design techniques and for transistor reliability and bandwidth extension to meet the desired performance. Multiple techniques can be used simultaneously, and the higher the bandwidth, the higher the complexity of the design. With that, thank you.
Thank you, Bob.